the organizers of this conference for giving me the chance to give this lecture. And well, as I said before, I will speak about the holonomy of the Bismut connection on complex submanifolds. And this is a joint work with Raquel Villacampa from Spain. Okay, so I will begin by making a few outlines of the talk. I will talk first about the holonomy group of a linear connection, and then we'll move on to recall some notions of Hermitian geometry. Then we will recall the Bismut connection on these Hermitian manifolds, and then we will move to the setting of complex submanifolds, where we will study some of the properties of this connection there in this family. Okay, so to begin, I will recall what's the notion of the holonomy group of a linear connection. So we begin with any connected manifold, and we consider there a linear connection. I mean, it's a connection on the tangent bundle of the manifold. We fix any point in the manifold, and we consider a gamma a piecewise smooth curve which begins and ends in P. It's a lasso, I think it's called also. So as we have the connection, we also have associated the corresponding parallel transport along this curve, along this lasso, and this defines an endomorphism from the tangent space at P to M, an endomorphism there, and which simply what it makes is the following. We consider any tangent vector to M at P, and we consider the parallel translation of this vector along, in the other sense, this one, we move along this curve, and we see where it ends, where it lands after this whole trajectory, and it begins in another place. So it defines a function of an endomorphism there, and it can be seen easily that this is a linear transformation, and it's also invertible. And by definition, it's invertible because you can travel the lasso in the opposite sense, and then we have the identity when we compose both. And moreover, we can compose two of these linear transformations, and it corresponds to taking the parallel transport along the juxtaposition of these two curves. So the set of all these endomorphisms of the tangent bundle, tangent space at P on M, is a group, and it is called the holonomy group. So it is the set of all these endomorphisms defined by parallel transport, and it is a group with a composition. And it is contained in this general linear group, dimension M. And if we consider two different points in M, we can see that, well, as there always is a curve joining P with Q, we can see that the holonomy group based at P is conjugated to the holonomy group based at Q inside this general linear group. And so they are all isomorphic. So we can speak simply of the holonomy group associated to the connection. So with no dependence of the point. And it can be seen that it is always a Lie subgroup of this general linear group. For instance, if G is a Riemannian metric, we know that we always have associated the Levi-Civita connection, which is the only connection which is compatible with the metric, and it's torsion-free. And in this case, the holonomy is contained in OM. It's these endomorphisms are orthogonal, and moreover, it is contained in SOM whenever M is orientable. Just to say a few words about this Riemannian holonomy, it was proved by Berger in 55, the last century, that the possible holonomy groups of a Riemannian, simply connected, irreducible, and non-symmetric Riemannian manifolds are all in a very short list. These are the following possibilities. It can be contained in UN if in dimension 2n. These manifolds are called Keller. It can be contained SUN in dimension also 2n, and in this case the manifold is called Calabi-Yau. It can be contained in SPN in dimension 4n, or in this group SPN times SP1, also in dimension 4n, and there are also two exceptional Lie groups, G2 and spin 7 in particular dimensions, 7 and 8. Well, Berger gave this list, and it was at that time it wasn't known yet if there were some manifolds which actually had these groups as their holonomy, and well, in several years later, it was proved that all of them appear effectively as holonomy groups. For instance, Yau gave examples of this, well, and when he solved the famous Calabi-Yau problem, and several other where G2 is actually very much studied, and Juiz gave the first compact examples of these manifolds, and well, but I mean that we can see that when there is a reduction of the holonomy, when it's not generic, when this holonomy reduces to a proper subgroup, it's because it reflects that there are some special structures, special geometric structures on the manifold. In this case, for instance, the parallel, the Hermitian, the fundamental to form is parallel. Here we have also that, along with Ricci flatness of the metric, and here we have three possible parallel Keller forms, and so on. So the reduction of the holonomy reflects important special geometric structure on the manifold. So, but we will not speak about the Riemannian holonomy in this. We will focus on other connection which will be introduced later. But just to mention, one way to compute the holonomy group is given by the Ambrose-Singer theorem, which it can take several statements, but one that we use is that the Lie algebra of the holonomy group of a linear connection is generated by the curvature. The Lie algebra of the holonomy is generated by the curvature endomorphisms, well, these ones, and the covariant derivatives of this endomorphism. This is the curvature endomorphism, which I can take also its their covariant derivatives, and all of these generate the Lie algebra of the holonomy group. It's not very easy to try to compute the holonomy using this theorem, because in general this tensor, the curvature, is very complicated on a general manifold. But for some cases, for homogeneous spaces mainly, or Lie groups, we can use this property in order to compute the holonomy, and so we will be using this later. Okay, so as I said, whenever we have a Riemannian manifold, we can work with the Levi-Civita connection, which is the most natural one, and it's a very important. With this Levi-Civita connection, we can define the sectional curvature, the Ricci curvature, all the things that we study in Riemannian geometry. But sometimes when there is a some extra geometric structure on the manifold, sometimes this Levi-Civita connection does not get along well with this connection, with this structure. So one tries to consider another kind of connections which are compatible with this structure. Generally, we lose something. It will not be as nice as the Levi-Civita. For instance, they will generally have a torsion different from zero. But so we can ask if we have some given structure on the manifold, we can ask if there is a special connection which preserves, in some sense, this structure and which has some good properties. And in general, the answer is yes. For instance, a nice property for a connection on a Riemannian manifold that one can ask is the following: we can ask the connection to be a connection with skewed symmetric torsion. This means, well, first I recall this is the torsion of a connection. It's given by that expression, and we can contract it with the Riemannian metric. In this way, we have T, and we put contact with this X using the metric, and we have this one, which is also called the torsion. And these special connections are when this torsion is a three form. Well, so we know that this is always skew symmetric in Y and Z, because this is skew symmetric in Y and Z. But we don't know anything in general with X and Y. But whenever this is a free form, we will call the connection with the skew symmetric torsion. And these are quite important in many places in geometry, because, well, it can be computed as this in terms of the Levi-Civita connection and this three form. In fact, any three form gives rise to a connection with the skew symmetric torsion using this formula. So, but if we have some previously given geometric structure, we should choose this three form in such a way that it is compatible with the structure. So that is another problem, because three forms, there are many. But one important property that they have is that this new connection has the same geodesics as the Levi-Civita connection. Okay? So, well, we will study one of these connections on the setting of the Hermitian manifold. So I recall a little bit about that, although most of you already know this. If we are given a smooth manifold, we will say that an almost complex structure on this manifold is a tensor in the tangent bundle, such that a square is minus identity at any point of the manifold. In this case, the dimension of the manifold is even, and M has to be orientable. And well, and when this almost complex structure satisfies an extra property, well, if one considers this complicated expression in terms of the endomorphism J and the bracket on the tangent bundle, if this expression, which is a tensor called the Nye-Noise tensor, this vanishes identically, it is then J is called also integrable or simply a complex structure on the manifold. Well, the well-known Nylander-Nirenberg theorem states that a real manifold admits an integrable, almost complex structure if and only if M is a complex manifold. So this means that there is an atlas of holomorphic charts with holomorphic transition functions. Okay. One could say a lot about this, but I guess most of us know. It is another problem that I would like to mention is the following. There are examples of four-dimensional real manifolds which admit almost complex structures, but cannot have any structure of complex manifold. It can be proved using the classification of compact complex surfaces. But no such example is known in dimensions higher than or equal to 6. So in higher dimensions, we don't know yet any example of a almost complex manifold which cannot admit a structure of complex manifold. One famous example is the S6, the sphere S6. It has an almost complex structure, but and there are many of these, and they are all the known ones are not integrable, but it is not yet known if there is one which is integrable, even though there are some papers which say that it admits, or others say that it doesn't admit. We don't know yet what happens. Okay, well, but that was a digression. So I go back to our study of the connections. So this is only the complex manifold. We add some Riemannian metric now. Riemannian metric on an almost complex manifold is called Hermitian or almost Hermitian, depending on whether on J being almost complex or complex. If J is orthogonal with respect to the metric, or equivalently if it is skew-symmetric. It's the same in this case because J squared is minus the identity. In this case, omega, given by this, the contraction of the complex structure with the metric, is a two-form called the fundamental form of the Hermitian manifold. And it is well known the most important family of these Hermitian manifolds are those, the Keller ones, which are given by the Hermitian manifold such that the fundamental form is closed. In fact, there is something more general. If we have an almost Hermitian manifold, we have that the complex structure is parallel if and only if this Nyanoid tensor is 0, so that J is integrable and the form is closed. So in this case, in any Keller manifold, we have that the J, this complex structure J, is compatible with the Levi-Civita connection. And it's only in those cases, only for the Keller manifolds. And these are very nice. They have been much studied. There are a lot of papers about this and books and many things because they are Hodge theory and many other things. They can be studied from the point of view of the differential geometry, complex geometry, symplectic geometry, algebraic geometry, and many others. But as one likes. For instance, one nice property is that if we have a compact Keller manifold, then the odd Betty numbers are always even, which is a very nice property. So the existence of this structure imposes restrictions on the topology of the manifold. However, there are another families of interesting Hermitian manifolds which are not Keller. They're always defined in terms of the derivative of the form or the exterior derivative or the covariant derivative of the form. In this talk, we will consider two of these cases. But first, I will introduce the connection that I'm interested in. It's the Bismut connection. Bismut proved that there exists a unique, given a Hermitian manifold, there exists a unique linear connection which satisfies two things, two conditions. It is Hermitian, meaning that both the complex structure and the Hermitian metric are parallel with respect to this connection. And also the torsion is totally skew symmetric, as we said before. This torsion is actually a three form. And moreover, it can be seen that, sorry, this is not F, it's an omega. Omega is the fundamental form. F was from another place, but anyway, and here again. And here again, I have to put it. Okay. Well, as I said before, we can always obtain the expression for this formula, for this connection using this formula here. And well, this connection depends both on the complex structure and the metric, because we can have a complex manifold, we put different metrics and Hermitian metrics, and the connection will change, and their properties will change also. Okay. One important thing is that this condition here implies restrictions on the holonomy group of this connection. As in the case before with in the Keller case, we have this, we have also the metric is parallel, and we knew that the Riemannian holonomy is contained in UN. Here it happens the same. The holonomy group of this connection, this Bismut connection, is contained in UN, where the dimension of M is 2n. I mean, n is the complex dimension of the manifold. So this was introduced by Bismut using some, I don't recall well, it's studying some kind of index on complex manifolds, but it seems that it was also introduced some years before by Strominger in some context of theoretical physics. And now there is a group of geometers which say that this connection should be called the Strominger connection instead of the Bismut connection. But anyway, I stick to the name that is most familiar to me, at least. In theoretical physics, sometimes it is called the KT connection, meaning Keller with torsion. And the study of manifolds endowed with this connection is called the Keller with torsion geometry. And there are some cases which are of particular interest. For instance, Calabi-Yau with torsion manifolds. These are the manifolds which its Bismut connection has holonomy contained in SUN, the same as in the Calabi-Yau for Riemannian holonomy. It seems that they appear in heterotic string theories. I know nothing about that, but it seems that they are interesting in this setting. We also have what are called the SKT manifolds by strong Keller with torsion. And well, this is not related to the holonomy, but it's important also. It's when the torsion three form is closed. And we also have manifolds with parallel torsion, and is when the torsion three form is also parallel. These are quite interesting also. In this case, the curvature has some additional symmetries. Yes, I see. Raimundo, you want to say something?
I wanted to ask, so what's the connection of the holonomy of this connection and the holonomy of the Levitch-Vita connection?
There are not many.
So you can't infer anything about the holonomy of either by knowing the other one?
At least I haven't. I wasn't able to do that. It's another world, but probably there are some connections, but I don't know how to infer anything from one to the other.
Okay, thanks.
Okay, thanks. And Okay, in this talk, we will talk a little bit more about these ones. For instance, I recall a result from Fino and Grancharov, where they prove the following. If you have a compact complex manifold which admits a nowhere vanishing holomorphic and zero form, this means that the canonical bundle is holomorphically trivial. Then, if you find a Hermitian metric G such that the holonomy of the Bismut connection is contained in SUN, then this Hermitian structure is conformally balanced. This means that it is conformal, it's a multiple with a positive function of a balanced metric. In particular, this complex manifold admits a balanced Hermitian metric. What is balanced? Balanced means that not the top power, but the previous one, if in dimension 2n, this is 2n, if you take the power of omega with itself n minus 1 times, this is a closed form. Maybe another way to see it, which is equivalently, which is simpler to understand, is that omega is co-closed with respect to this is the codifferential induced by the metric in our manifold. So this is one of the classes of almost Hermitian manifolds given by Greyer-Vela. I think it's W3. Yes. So you can see if you obtain, if you have a reduction of the holonomy of the Bismut to SUN, then there is a balanced Hermitian metric. This is so it shows that there is some kind of connection between these two conditions. So I will move now to a particular family of manifolds. I will speak about solved manifolds. These are some special compact manifolds which are obtained as a quotient of a simply connected solvable Lie group by a discrete subgroup gamma. So in this case, we have that the projection is a local diffeomorphism. It's covering, and also that pi 1 of this is isomorphic to the discrete subgroup. Okay, so these are important because they were used to produce a lot of examples and counterexamples in different places of geometry. For instance, the Calabi-Yau manifold, which was the first example of a compact symplectic manifold which does not admit any Keller metric, is an example of is given by one of these. It's a nil manifold. A nil manifold is the same as a solved manifold, but when G is a nilpotent Lie group, and they have many interesting properties. They are all aspherical and some other things, and they are determined by the holonomy, by the fundamental group. If two solved manifolds have the same isomorphic fundamental group, then they are diffeomorphic. Okay, so we will consider invariant structures here on solved manifolds. An invariant Hermitian structure. This means that the complex structure comes from a left invariant integrable almost complex structure on the Lie group. Left invariant means that the left multiplications are holomorphic maps in G. This is the same as an endomorphism of the Lie algebra of the group, such that its square is the minus identity and satisfies the vanishing of the Nye-Noise tensor only for elements in the algebra. And also, we ask the Riemannian metric to be left invariant. Invariant on this quotient, it means that it is induced by a left invariant Riemannian metric on G. This means that the left multiplications are isometries of the metric. And this is the same as having an inner product on the manifold compatible with this endomorphism, which we had before. So we can work at the level of the Lie algebra. So what happens also when we have this kind of invariant Hermitian structures on the solved manifolds? Well, a first result was given by Fino, Parton, and Salomon in the beginning of this century. Then they say that they proved that if we have a nil manifold, this is given only for nilpotently groups, nil manifold endowed with an invariant Hermitian structure, then these two conditions that I mentioned before to have a reduction of the holonomy of the Bismut to SUN and the metric being balanced are in fact equivalent in this family of complex manifolds. So, so it can be, it is easier to study this condition, whether the metric is balanced or not. So we have a precise description of the complex Hermitian nil manifold, which admit whose holonomy of the Bismut connection reduces to a subgroup of SUN. And so this follows by the theorem of Salomon, which establishes that any potently group with which admits complex structures has a basis with some very nice properties, and we can deduce this from the existence of this basis. We don't know what happens in general with soft manifolds, but we will talk about this later. But a little later, some years later, Ugarte and Villacampa studied these nil manifolds endowed with this kind of invariant structures, invariant Hermitian structures, but only on 6 dimensions. And in their study, a special class of complex structures appeared. This special class of complex structure was introduced 20 years before that by Barberi, Dotis, and Miatello. Yeah. They are called abelian. Those are complex structures on a Lie algebra which satisfy this condition. This condition implies the vanishing of the Nye-Noise tensor, which is stronger, in fact. And also these manifolds, these Lie algebras with this complex structure have some very nice properties. They have been used to produce some examples of HKT metrics, or they have been quite used, and also in hypercomplex geometry. For instance, if J is an abelian complex structure on this Lie algebra, then G has to be two-step solvable. This means that the commutator ideal is abelian, and also the center of the Lie algebra is J invariant. In particular, its dimension is even. Okay. So I come back here. I said that in this paper, Ugarte and Villacampa studied the holonomy of the Bismut on 6-dimensional nil manifolds. And these complex structures, the abelian ones, play an important role. In fact, let me state the result. It says that if you have a 6-dimensional nil manifold endowed with an invariant Hermitian structure, then the holonomy of the Bismut reduces to a proper subgroup this is important, to a proper subgroup of SU3, if and only if the complex, the complex structure is abelian. So if it reduces to SU3, it happens if and only if the metric is balanced. But if it reduces to a proper subgroup of this SU3, there is an extra condition. It only occurs when, this only happens when J is abelian. So Raquel Villacampa came to Córdoba some years ago, and then we were trying to understand what happened in this. What is the key point in this reduction? Was this only happened because it was in dimension 6? Or it only happened because we are considering nilpotently groups, or because J is abelian? So we wanted to understand that. And we also see that there is an example of a 6-dimensional solved manifold. So we moved from nil manifold to solved manifold. We're still in dimension 6 with an invariant balanced Hermitian structure such that J is abelian, the same as here, but the holonomy did not reduce to a proper subgroup of SU3. So there is some kind of difference between these two results, between the setting of complex solved manifolds or complex nil manifolds. But in fact, after a lot of work, we could see that we could give the answer to the previous question, what was the key point, and we obtained the following theorem. If we have a 2n-dimensional solved manifold equipped with a Hermitian structure invariant, or this is always invariant, even though I don't say it, such that we ask that the complex structure be abelian and the metric balanced. We can control how much this group reduces, taking into account the dimension of the center of this manifold. So if the dimension of the center is 2K, it is always even because the center is J invariant when this is abelian. So if the center has dimension 2K, then the holonomy of the Bismut connection reduces to a, is contained is SU of n minus K. So the bigger the center, the smaller the holonomy group of the Bismut connection. So in this way, we can understand what happens in both of these cases, because if you have a nil manifold, a nilpotent Lie algebra always has a non-trivial center. So when it is abelian and unbalanced, it is balanced because it's reduced, then it will reduce to a proper subgroup of SU3, because the center will make the holonomy to be smaller. And also in this case, what happened here is that in this case, this solved manifold, the corresponding Lie algebra has trivial center. So there is no, it reduces to SU3, but not to a smaller subgroup, to a proper subgroup, because there is no center. So in the proof, we use some of these lemmas. Well, but I don't know if it is. Well, we give a condition for the unimodular Lie algebra, and when we say when this Hermitian structure is balanced. On a unimodular Lie algebra, it happens if and only if there exists an orthonormal basis of G such that the sum is 0. J of EI with EI, the bracket, the sum is 0. And also, if we consider a Hermitian structure on a Lie algebra with J abelian, then the only one forms which are parallel are the ones which are G-dual to elements of the center. So we see that all the elements of the center are parallel with respect to the Bismut connection. So there is a lot of parallel things, and that makes that the holonomy reduces. So, and then these are only the first steps in order to prove the main theorem, but the other are more technical, so I don't write them, but this is the main part. And this is what I said before. Whenever we have a nilpotent Lie algebra equipped with a Hermitian structure such that the metric is balanced and the complex structure is abelian, then the holonomy of the associated Bismut connection will reduce to a proper subgroup of SUN, and this is simply because the center of a nilpotent Lie algebra is non-trivial. Okay, so I have some more minutes. Okay, so so far we have worked always here with balanced metrics. So we will move. Well, I think I will skip this. This is an example of how to construct many nil manifolds equipped with these structures. One with abelian. It's a way to construct nilpotent Lie algebras equipped with Hermitian structures such that the metric is balanced and the complex structure is abelian. We begin with the commutative associative algebra. We take twice the double, A plus A, with this Lie bracket using the product of the algebra. And one can prove that this is in fact a Lie algebra. The interesting ones for us are the nilpotent ones, because these are not the only cases when these are unimodular. There is this one to give the multiplication by I in the complex numbers is an abelian complex structure on this Lie algebra, and it always admits a nice Hermitian metric, and one can give exactly the establish when these admit an abelian balanced Hermitian structure, when there is an orthonormal basis of the associative algebra such that this condition is fulfilled, and this is easy to establish in low dimensions. There is a classification of associative algebras in low dimensions, and we can see which ones admits this kind of basis. And whenever this Lie algebra has rational structure constant, the associated Lie group will have some co-compact discrete subgroups. So we have many examples there. And what happens when the metric is not balanced? We will move to another family of Hermitian manifolds, which is in some sense complementary to the balanced ones. These are called the Weismann manifolds, but we begin given by the definition of locally conformally Keller. Well, the name says everything. Now, a Hermitian manifold is called locally conformally Keller if each point has an open neighborhood in which the metric is conformal to a Keller metric. So we can multiply the metric in that open set by a positive function such that the new metric is Keller. So this is local, but one can put everything together. The derivative of these functions, fi, they all glue together to give rise to a well-defined closed one form on the manifold, which satisfies this. This is equivalent to have this open covering on the manifold with the existence of this closed one form, which satisfies this. This form, theta, is the Lie form and is given by this expression. And this family of manifolds is complementary to the balanced ones, because in that case, this theta, the Lie form, is 0. We don't want here these ones to be 0, because if theta is 0, then the omega is 0, so it is Keller, and we want non-Keller manifolds. And whenever this Lie form is parallel with respect to the Levi-Civita connection, we say that this manifold is Weissman, because he was the first one to study this and he obtained a lot of results about these manifolds. They have some important properties, topological properties, which make them quite different from the Keller ones, but they are still being studied, but they are well understood so far. But we are trying to study now with Raquel the Bismut connection on these manifolds. And one can see that this Lie form is parallel with respect to the Levi-Civita connection. That is, this is Weissman, if and only if the Lie form is parallel also with respect to the Bismut connection. So, instead of studying the parallelism with respect to the Levi-Civita connection, we can move to the parallelism with respect to the Bismut connection. And this is better because since this is compatible with the complex structure, we have also that J of the Lie form is also parallel. So we have more parallel things here. And as a consequence, we can see that the holonomy of the Bismut connection is containing UN-1 when the manifold is 2n. And also this is very nice because in this case, the torsion 3 form of the Bismut connection is parallel. It's one of the nice families of Bismut manifolds, Hermitian manifold with respect to the Bismut. And it has some nice, the curvature tensor has nice symmetries with, in this case. And we can see there is also a tensor which is important. It is this one, is practically the same as the complex structure J, but it's modified a bit so that instead, now that this phi vanishes on A and JA, but it is equal to the complex structure if X, this is not if, well, if X is perpendicular to A and JA. Why this is important? First, because it is parallel with respect to the Bismut connection. And because we can say that we can study the Bismut connection in general for these Bismut for these Weissman manifolds, and it is this given in terms of the bracket, the complex structure, and this tensor phi. Well, it's not necessary to understand all of this, but we can give a quite precise description of the Bismut connection of these manifolds using this tensor. And moreover, it is very important in the case of solved manifolds. When we have a solved manifold equipped with a invariant Weissman structure, again, we can work at the Lie algebra level with a former student of mine, Marcos Auriglia. We were able to give a detailed description of the structure of the Lie algebra G when it admits a Weissman structure. And using this structure, we were able to compute the curvature tensor of this Bismut connection on the Lie algebra. And it turns out that these endomorphisms are always a multiple of this parallel tensor phi. So in particular, every curvature endomorphism is parallel with respect to the Bismut connection. And if we recall the Ambrose-Singer theorem that says that the holonomy Lie algebra is generated by these endomorphisms and their covariant derivatives, so all these are multiple of phi, but all of them are also parallel, so their covariant derivatives are 0. There is nothing extra to be added, so we can say that the holonomy algebra has dimension 1, and it is generated by this tensor phi. So there is a strong reduction of the Bismut holonomy, but we can see, it is easy to see that this phi clearly has to be in UN, is in UN, but it is not in SUN. So there is a strong reduction of the holonomy, of the Bismut connection, but this subgroup, this holonomy escapes from the SUN. It does not reduce to a proper subgroup of SUN. So to finish, we state a conjecture that the reduction of the holonomy group of the Bismut connection to a proper subgroup of SUN in Hermitian solvmanifolds occurs only, or happens only, if the metric is balanced. We have we believe that it is so, but we were not able to prove it yet in full generality. Okay, and that is all I wanted to say. Thank you very much.
Thank you, Professor. Any questions or comments? Please, Adrian.
Hi, Adrian.
Hello, hi.
So I'd like to know if in the context of solvmanifolds, there is a characteristic foliation in the setting of Weismann manifolds.
Yes.
Okay? In the setting of new manifolds, the characteristic foliation is not regular.
I don't know if it's always regular.
There is a classification of homogeneous Weismann manifold, but in the classification, it is used the fact that the foliation is...
Yes, but these Weismann solvmanifolds are not homogeneous Weismann.
Okay.
As studied by Moroianu. Okay. No, these are not the same. They are not so nice.
Okay.
Those ones.
But so there is a relation between Weismann solvmanifolds and Sasaki manifolds.
Yes. Also, there are many relations with that, and there are open problems also here. We know that Weismann nil manifolds, a nil manifold can admit a Weismann structure, not necessarily invariant, if and only if it is a quotient of a Heisenberg group times R.
Okay.
That was proved by Bazzoni, but it is not known yet for a general LCK manifold. That is much more complicated.
Okay.
So, well, it is believed that if you change Weismann, that the only nil manifolds which admit an LCK structure, only LCK, have to be also a quotient of the Heisenberg times R.
Okay.
That it is not known yet.
Okay. So thank you.
Thank you. Raimundo,
please.
I see you. You're muted.
Sorry. I was just saying that I have a series of questions, but the very first one that I wrote, you later posted a proposition that kind of like make it appear that it's false, my guess. So can you give me an example of... So the question is on the relation of this holonomy between for the Levitch-Vita connection and the holonomy for the Bismut connection.
Yes.
So my first guess would have been that the invariants of these guys are the same. And you posted a couple of examples where they are, but then later you posted a proposition when they are. So I wonder if you have an example where you have some tensor that is not invariant for one and is invariant for the other one. You have a proposition where it says for this theta form.
This J theta.
Right.
In general, this is parallel with respect to the Bismut connection, but in general, it is not parallel with respect to the
Riemannian. That one would always be parallel for the Bismut connection?
Yes.
In any case?
Yes, because of this. Since J is parallel, then and theta is parallel, we also have the J theta is parallel. But in general, it doesn't happen for the Levitch-Vita.
For the Levitch-Vita.
For the Weismann, if the manifold is dimension 2n, the Riemannian holonomy of the Weismann is containing O 2n minus 1. there is a reduction in one dimension because of the leaf form being parallel, but not more.
Okay, I guess I have to think. I would not have expected this to happen when you have the same geodesics, but okay. So I guess I'm just confused.
No, but you see the one in general, the holonomy, even if there is no reduction, the holonomy of the bismuth is always containing UN, and that is much stronger than.
That's a good example. Yeah.
Than in general, the general Weissman is in O2n-1, which is much bigger.
Okay.
Okay.
Then I have just a curiosity. Before your theorem, when you posted a theorem for reduction on SU3, so for proper subgroups of SU3 in the case of Néel manifolds.
Yes, I'm arriving there.
I wonder
here.
How hard is that theorem? And there aren't that many subgroups of SU3. So if you just impose that you are reducing to a proper subgroup of SU3, can you just not do it by hand?
I have seen this. I've studied their paper. There is a whole list of six-dimensional nilpotent Lie algebras, and they also studied all the complex structure there.
Right.
So they make a study, let's say case by case, and they see that first they consider all the nilpotent Lie algebras which admit a balanced Hermitian structure. And they're using this Ambrose-Singer theorem. They study their holonomy, and they realize this thing that there is exactly proper reduction when the J is abelian, but checking case by case.
Yeah, that was my guess, that you could do this case by case quickly in this case.
Yes, but then what we try to do with this other theory was avoid this case by case and try to generalize that, understand what happens there.
Sure. Thanks.
Thank you.
Any more questions or comments? So let's thank to the Professor Adrian.
Okay. Thank you very much.